Oh, is it the last week of chemistry or? Morgan. What did you decide to come? I'm going to make sure this won't be a foot there, and we will get started.
That's what I did for the first week like that.
Name it. David? Alex? Name it. Okay. Have you guys gotten into polyatomic ions yet?
Yes.
Am I gonna bother you? Let me know if I do. Okay. So I'll run through just a broad overview of the different naming concepts you guys have covered. If, as always, if anything comes up, if you have any questions, stop me. Otherwise, I'll keep on going. And then once we get through that, we'll do a couple of naming examples, and then we'll do a couple unit conversion examples as well to keep that fresh. That makes sense. Is there anything in particular in naming that is giving you difficulty, or just in general?
In general.
Okay. Naming. Start with ionic. We talked about this a little every day last week. Last week. So as a reminder, ionic is going to be a non-metal with a metal. Ion. Remember, we have the cation, which is the positively charged species. That word again. And the anion, which is a negatively charged species. When we're naming the cation, we say element. Element. Whereas the anion, we're going to say element ide. So if we have NaCl, if we were to name the ions here, we have the sodium ion, and we have sodium and chlorine. Chlor, instead of ene, we're going to replace the ending with I. Ion. And we can say cation and anion here. I believe. So we have a sodium cation and a chloride anion. Does that make sense? Fantastic. So when we name them together, we're going to have our cation, anion, I. And once we start talking about the polyatomic ions, this also could be height or H. Where we're at right now, cation, anion, I. So for example, this would be sodium chloride. As a note, remember when we're naming ionic compounds, we do not identify quantity. Does that make sense? Right. So if we have, for example, AlBl3. Initially, we can know that this is going to be an ionic compound because we have a metal, the aluminum, and a non-metal, which is the chlorine. Take that back to your periodic table and know the locations of your metals and non-metals. So we would not say that this is aluminum trichloride. That would be not correct. couple of you guys hear this stuff? A couple of other bits with your ionic compound. Hydrates. Talk about this bit, yeah. So hydrates happen when ionic compounds are attracted to water. And depending on the ionic compound, that determines how many water molecules it will be attracted to. So, for example, if we have MgF2, how would we name this as an ionic compound? Right. Magnesium. Our cation, our anion, we change the ending to IUC. Now you may see a compound that looks like this. So that dot, and then H2O. And we can have different quantities of water. So if we had this, that would be magnesium chloride hydrate. If you saw a compound with 4 water molecules, we would have that compound tetrahydrate. We'll get into those prefixes when we talk about the covalent compounds in a minute. So it's important to identify the number of water molecules, but you're not going to identify the actual ion. Any idea why we don't identify the ion? Any thoughts? Yeah, so we identify quantities in covalent compounds, but naming it with the quantities wouldn't make it a covalent compound. Let's look at calcium chloride. Calcium chloride. I want you to use what you know from the periodic table to try to come up with the ionic formula of calcium chloride. You guys haven't done a lot with this yet, so I wouldn't share this stuff with you. We have to do it right away. Does anybody have an idea of what the ionic formula would be for calcium chloride? Right, so you have calcium, and calcium is in the second group, the second column, so that means that it has positive 2 charge. And chloride is in the 7th group, and it has a negative 1 charge. So when these come together, they want to find a neutral charge. So if we have a negative 1 here and a positive 2, how many of each do we need to cancel the charges out? Does that make sense? 2 negative charges to cancel out the 1 positive charge. Any questions there? As a trick, if you can write out your ions, you can then switch the charges to the opposite substance. It will almost always work. Occasionally, you'll have to simplify, because remember, ionic compounds is always in the most simplified form. So, for example, if this was -2 and +4, then we would have to simplify it to be 1 and 2 instead of 2 and 4. Does that make sense? Likewise, you want to be careful with going the other direction for that reason of simplifying things out. So if you had something that, let's say we had, I'll do one more explanation and then we'll do that. The last concept that we want to talk about with ionic naming are metals that consume multiple charges. metal. What I mean by that is, depending on the metal, sometimes it can take different charges. So you know that these over here, you're going to have +1, +2. Once you get into the transition metals, you can have different charges on the metals depending on what they're bound to. So, let's say we have iron chloride, or iron chloride. So in this case, we want to be specific about what the charge is on the iron when we name it. So in this case, we know that chlorine has a -1 charge. We have 3 chlorine. So what does the charge need to be on the iron? We know that chlorine, when it becomes an ion, when it becomes chloride, has a -1 charge. And we have 3 of them. What does the charge need to be on the iron? So we're going to say this is iron 3 chloride. Whereas this would be iron 2 chloride. This is a fairly new standard of naming. You may also see this as ferric chloride and ferrous chloride, but you wouldn't be tested on that naming scheme. You'd be tested on the chromium. Any questions on this? Any questions on naming ionic compounds?
Going from the FeCl3 to iron chloride.
Yep. So we know that chlorine, when it becomes an ion, has a -1 charge. And we have 3 of them, shown in our subscript. We know when these come together, they have to be neutral. Right? Okay. So we have chlorine, 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 and each of these contribute a -1. And our iron needs to help us get neutral. We need a +3 to cancel out those. Okay. 3 -1. Cool. Ready to move on to covalent compounds? Yes? Start off with the basic ones, and then we will get into hydrocarbons and then polyatomic. So for our covalent compounds, we need to identify which prefixes to be using. Because remember, for covalent compounds, we're going to be identifying the quantity of each of the atoms. Ionic compounds, we don't, because they're fixed with their charges. Sodium and chloride are only ever going to come together at a 1-to-1 ratio, so we don't need to say how many of them. You would never have NaCl2 because that wouldn't be. Covalent compounds, we have our prefixes, so we have 1 or mono, 2 di, 3 tri, 4 tetra, penta, hexa, hepta, octa, nona, and deca. So, for example, how would we name NO2? when we name, we're going to name mono, prefix, atom, prefix, atom. And as a general rule, if the first atom is mono, I'm going to drop the prefix. We're also going to drop double letters. I'll show you that in a minute. First atom, we only have one of them. We're going to drop the prefix. We're also going to drop double letters. So with that information, what do we think NO2 will be naming wise? Be careful if you're starting to think polyatomic ions, you do not have a charge on them. Nitrogen dioxide. Dioxide. So rather than saying mononitrogen dioxide, because the first one only has one, we can drop the mono, so we say nitrogen dioxide. What if we had N2O4? N2O4, what do we think there? Alex? No? What's our prefix for 2? Dinitrogen. Rather than saying tetraoxide, I'm just going to say tetroxide. If you were to answer saying dinitrogen tetraoxide, you wouldn't be much wrong, but as a convention, drop the double one. That is tetraoxide to tetroxide. What if we have steel? Carbon monoxide. Carbon monoxide. We're not going to say monocarbon because it's the first element. And we're not going to say monooxide because then we would have 2 of them. Carbon monoxide. Fun fact, equal. Any questions for this guy? Now let's talk about hydrocarbons. Hydrocarbons are uniquely named separately from our normal conventional naming. And it has to do with how many carbons we have. Or the name by number carbon and type of bond. We'll start with types of bonds. We can have alkanes. Who remembers what an alkane is? So alkanes have all, and I'll show you the trick in a minute, all single bonds. What about alkenes? What do we know about alkenes? Not all double, but they have at least one double bond. going to be alpine. And what do you think this is? As a trick, we all know the order of the vowels, A, E, I, O, U, sometimes Y. They go in that order. You have A, E, Y. Does that make sense? Perfect. Now, we also care about the number of carbons. So our prefixes for one carbon is met, 2, cope, 4, bute, 5, pent, 6, F, F, ox, known, and F. So what you'll notice is that outside of these first 4, they're the same as the prefixes. That makes sense. When we're naming hydrocarbons, we're going to start with the number of carbon prefix and end with the type of bond ending. So we have prefix from the number of carbons, and then we have suffix from the bond type. That's how we do it. So for example, if I have butene, Bute means that we have 4 carbons, and ene tells us we have at least 1 double bond. And so what you guys are going to be covering, all of your hydrocarbons will just be straight chains. This tells us that we have a carbon, bound to a carbon, bound to a carbon, bound to a carbon. We have 4 carbons bound together, and we have at least 1 double bond. If you go further with chemistry, you will start to decipher between the different kinds of butene. So for your guys' purposes, it doesn't matter if you want to put the double bond there, or there, or there. They are all butene. And the rest of the carbons are saturated with hydrogen. Remember, the carbon's only going to make 4 bonds. So we're going to fill in hydrogens to make sure that all of our carbons have 4 bonds. Any questions on this? We'll also start to see this form too. For each of these vertexes is going to be a carbon, and each line is a bond. So this would be another way to draw butene. If that makes sense. Okay. So I have E3 H I want you guys to try to work out what this name is. C3H6. So one part of the name you'll be able to get pretty quick. The other part you'll have to do some thinking. Even if you've only got half of them, let me know. Reason, right? You got half the name? Pro. We've got that's half of it. Now you gotta figure out the other half. Anybody figure that one out? You know it's gonna be pro. Also, I like to think there'll be a little bit where you have some difficulty getting those four. I like to think pro is a plane with color. No? Nobody? Okay. That's also, it doesn't look like a plane. Okay. Morgan, did you get it? Okay. All right. So we've got carbon, carbon, carbon. So there's our 3 carbons. Now we just start putting in hydrogen and see where we end up. Oh, the hydrogen here, here, here. There's 3 of our hydrogens. And maybe we'll put a hydrogen here, here, here. There's all 6 hydrogens. That doesn't work. All right, because this carbon needs to have 4 bonds. Right now we can't because then these will have 5 bonds. So we play around here. Well, what if we put a hydrogen here? So this one's got 3 bonds, and this one's got 3 bonds. So we put a double bond there. And here. We've got 1, 2, 3, 4, 5, 6 hydrogens, 3 carbons. This carbon's got 1, 2, 3, 4 bonds. This carbon's got 1, 2, 3, 4 bonds. This carbon's got 1, 2, 3, 4 bonds. So all of our carbons have 4 bonds. We have 3 carbons and 6 hydrogens. What would we name this structure? A 33% chance of guessing right. Propene. Yep. Because we have at least 1 double bond. If you want a trick, we know that if we saturate, we're getting to maybe some bio terms. If we saturate this hydrocarbon, we fill it with hydrogen, we have C3H8. As a general rule, I wouldn't expect you to memorize this, but the number of carbons times 2 plus 2 for these straight chains. Well, let's talk about why real quick. So we know that every carbon, doesn't matter how long our chain is, if it's all single bonds, they will all at least have 2 hydrogens, right? 1 on either side. Except the 2 on the end, which have an extra 1. So there's our 2. So I knew that we had C3H8 and propane. And if we add a double bond, we have to take a hydrogen from each of the carbons next to it because they're both giving into that bond. That's why we use 2. Does that make sense? It is okay if that was tough. It is not to be tough. Not to get to thinking about it. What if I gave you that? What would we name this? Every first half ending. Daily. pentene. Yep. Pentene. 1, 2, 3, 4, 5. We know it's 10. We have at least one double bond. We know ene for our ending. So we have pentene. If I gave it to you like this, we would have 10 times. Cool beans? Kind of sort of. All right. You guys good with this right now? Now we get to one of my favorite topics. That as you keep coming, I will keep bringing up because you need to have these memorized. So real quick, what are polyatomic ions? What's that? They are fun to name. What are they? Polyatomic ions. Don't overthink it. What does atom mean? Atom. What does poly mean? Multiple. What does ion mean? What's that? Yeah, so it's a charged species, right? So it's multiple atoms with a charge. So multiple atoms with a charge. So I'm going to write a bunch of them on the board. These will be the most important ones. Sometimes professors will throw in a couple of others. If you did, make sure you know them. But these are going to be your most common ones. Oh. We have ammonia. Hydroxide. Nitrite. Nitrate. Carbonate. Bicarbonate. Sulfite. Sulfite. Sulfate. Phosphite. Phosphate. Isochloride. Chloride. Chlorate. These are what I would say are your most common and most important ones. But it's not just straight memorization. There are patterns to pick up on. Once you get that those down, a little bit about what those patterns are. charges, it's just as important as going the compound. Does anybody see any patterns? Do you see any patterns? Fine, you're on the right track. So Alex, for those of you here, said I for 2, H for 3. Fine. What we see, so you're right for nitrite, I for 2, H for 3. But over for phosphite, we have I with 3, H with 4. So the I and the 8 correspond to the number of oxygen, but it's relative. So it's not, if you have 8, you'll have X amount of oxygen. What we see is hypo something ice, then that something ice, something 8, and then per something 8. As we increase the number of oxygen, as we go down, we're increasing the number of oxygen. So that means you really only have to memorize one of these steps. Because if you can memorize nitrite, then you know nitrate has one more oxygen, and it's the same charge. So nitrite, nitrate, same charge. Phosphite and phosphate, same charge. Sulfite, sulfite and sulfate, same charge. A memory trick for your charges, for those three in particular. NSP 1, 2, 3. NSP 1, 2, 3. Your nitrite and nitrate have a -1 charge. NSP 1, 2, 3. Your sulfur-containing compounds, sulfite and sulfate, have a -2 charge. NSP 1, 2, 3. And your phosphorus-containing compounds have a -3 charge. NSP 1, 2, 3. Does that make sense? This full range will not necessarily actually exist. Right? It's more theoretical. For something like chlorite, it does. We have the full range. We can have hypochlorite, add an oxygen, we get chlorite, another oxygen, we get chlorate, another oxygen, we get perchlorate. But for something like nitrite or nitrate, we really wouldn't see hyponitrite or pernitrate in the real world. Okay. So these are covalent compounds that have a charge, they're ions, that then are attracted to other ions. So sort of a cross between your covalent and your ionic compound. Does that make sense? So these, the chlorine and these oxygens are covalently bound together. What would the ionic formula be for sodium phosphate A? Sodium phosphate. What do we think? Ryan says Na3CO4. How's that look? Okay. So we know that phosphate is PO4 3 minus. And we know that sodium, because it's a group 1 metal, has a +1 charge. So we can put these two to get NaCO4. Remember, you've got to double check to make sure you don't simplify it. What if we had calcium sulfite? Like that? Yeah, that's okay. Right there. And so 3. I would. Well, it's most important for you to add the parentheses if you're putting something here. Otherwise, it doesn't matter. If it helps you identify that you have a sulfite ion rather than calcium bonds with sulfur and oxygen, then feel free to put parentheses. It's not going to make it wrong. Why not? So if we say that calcium has a 2+ charge and sulfite has 2- charge, why don't we say that this is CH2 SN32? Right. Because even if we do this crisscross rule, we want to make sure that we're our most simplified form because it's an ionic compound. Does that make sense? All right. If we have iron 3 sulfide. I want you to come up with the ionic formula for iron 3 sulfide, iron 3 sulfite, iron 3 sulfate. Iron 3 sulfide, sulfite, sulfate. Anybody get it? How about the first one? Oh, still looking right? All right. We are finished. We do this take time, but it's the idea of your converging ones as well. I guess we don't have to do that. That's 3.5 grams of magnesium chlorate. All right. What do we think for iron 3 sulfide? Morgan. Fe2S3. So it ends in "ide," so we know it's not one of our polyatomic ions. We find sulfur in the periodic table. Find a fifth group. The fifth group is going to have a -2 charge. If our iron has a -3 or a +3 charge, and our sulfur has a -2, we flip it, simplify, we get Fe2S3. Anybody want to take a stab at iron 3 sulfite? David? Fantastic. Almost. SO3. So identical up here, except we have sulfite instead of sulfide. We have SO33 instead of F3. And Alex, what do you think for the last one, iron 3 sulfate? Perfect. So just like above, but we have SO4 instead of SO3. I know it's a lot of information. Make flashcards, write them a bunch of times, do what you need to do, but it's important to memorize your values. Any questions on these? No, then. Nothing well. Or good students, flashcards, put them. All right. Now, this final example for us. If I have 3.5 grams of magnesium perchlorate, how many atoms of oxygen do I have? So, what is our first step? Any ideas? Oh, I didn't. Yeah, that's okay. This is an extra advanced example. I should have given you one bit of information. And we are a little tight on time here. Eventually you'll be able to do this, but I'm going to tell you that the molar mass of magnesium perchlorate equal to 223.206 grams per mole. Very soon you will be able to do that. But even before we get to there, what should we determine first? Yeah, we should figure out what the hell magnesium perchlorate is. Anybody have any idea? No. So what would our charge be on a magnesium ion?
That's a plus two.
What is perchlorate? ClO4. What's the charge? Anybody already have it from his memory? Was that what you thought? Anyone? So when these come together, we get MgClO4 2. MgClO4 2. And now we're going to run that check. 3.5 grams. What were you going to do then? You do 3.5 grams. And we know our molar mass is 223.206 grams in 1 mole. Our grams then cancel. Who wants to give a stab at the next step? Now we're left with moles. How do we go from moles to atoms? From moles to Avogadro's number. Anyone remember what Avogadro's number is off the right?
6.822 times 10 to the 23.
10 to the 23rd particle per 1 mole. I'm going to say particles right now, and I'm going to say this in MC. Particles of MC. We have the grams of magnesium perchlorate, and we've worked our way into particles of magnesium perchlorate, or the compound unit. What do we have to do next? Probably a step that you guys haven't quite done, but one that I know you would be able to figure out. What is the question asking for? Atoms of oxygen. What unit do we have left right now after we cancel our grams and moles? We have basically formula units of magnesium perchlorate, right? So remember that MgClO4 2. This would tell us how many MgClO4 2s we have. How do we go from that to how many oxygen atoms? 1 MgClO4 2 is 8 oxygen. Does everybody see how that is 8 oxygen? So every chlorate ion has 4 oxygen. Then we have 2 chloride ions, so we have 8 oxygen. And you can do the math and figure it out. Any questions on this example here? Besides me getting this, you guys have a couple more. Oh, you have it? Yes, you're doing it right now. So, if you were to calculate all of that, you go over to the periodic table and you say, okay, we have 1 magnesium. So magnesium has a mass of 24.3050. And we have how many chlorine atoms? Chlorine has 2. So chlorine, 35.4527. 2 of those. last element is oxygen. We already said we have 8 oxygen. Oh, you would multiply that out, add it up, and you would get our 223 and 206. Might be a little off. The second or third decimal. Any other questions, comments, concerns? Yes. Electrons are a little different. I think she talked a little bit about that today. So let's say we have some mass of gold. Right, well, we know that gold, a one atom of gold has 79 electrons. So once you get to that atomic, then you can convert to your subatomic part. Basically, that would be the next step here. If for whatever reason I asked you how many electrons associated with oxygen atom, then we could go ahead and say, well, we know we have 8 oxygen atoms per unit of magnesium perchlorate, and every oxygen atom has 8 electrons, so we multiply it. Does that make sense? Any questions on any of the stuff we talked about today? I know it was a lot of information. No? Nothing at all? Do you guys have a good handle on everything? You know what all? You got it all memorized? The only thing we didn't talk about, which she covered a little bit, was functional groups. So, for example, ethanol and ethane, but I think she covered it.